last 5 lectures, we've dealt with instantons in particle mechanics, and we found that they have some very interesting properties, and they enable us to compute tunneling in a way that you would find very difficult to do otherwise. We're now going to turn towards quantum field theory. We've already seen an instanton, the O4 instanton, in a scalar field theory. But now we're going to do something that is much more interesting, and that's to do with multiple vacua in gauge field theories. So this will take us into QCD and other gauge field theories, but we will not be able to get directly into that in this lecture. What I will do is create the background for that so that we can take this up in the very next lecture. So for this, I will need to create some background and talk about spontaneous symmetry breaking, but very briefly. And so here goes. We've done all this earlier. Let me just set this. Okay, so gauge fields and multiple vacua will be what we will aim for. And if we get the chance, then we will talk about effective action, not in the next lecture, but perhaps the very next one after that. That is, if we get the chance. Okay, so let's go back to particle mechanics, and here's a particle on a circle. So it's being pulled down by gravity, F equals mg, and it goes around. And now you see it will swing back and forth like this. It will not know about what life is up over here. It will not have the energy to go all the way up. If you released it from here, then it will just go back and forth. But in fact, in quantum mechanics, it can pick up energy and go around once, go around twice, and maybe go around this way once, twice, thrice, an infinite number of times in either direction. So in this case, we have multiple vacua, and we will see how this is reflected in field theories, where we have a non-trivial topology in the space of gauge fields. And when we get talking about that, we'll talk about the Chern-Simons current and so forth. But that's for later. Now, do these have any implications for physical observables? Well, let's first consider a gauge field theory. Perturbation theory is all that we do when we do scattering theory, when we do, let's say, proton-proton scattering or electron-electron scattering or whatever. We always do an expansion in the small parameter, which is the coupling constant. But as we've discussed, the instanton can take us from one vacuum to the other, and this is completely non-perturbative. Perturbation theory will never allow you to do tunneling. Now, in addition to the instanton, there's something called the sphaleron, and this sphaleron, instead of making its way through like this, it sort of makes it over the top. But this is something that exists only in the standard model and gauge field theories which are similar to that. So here is a nice picture. You see that these are multiple vacua. There's a vacuum here, 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 and the instanton essentially tunnels through whereas the sphellaron goes over. And the sphellaron is actually responsible for baryon number violation in the Standard Model. And therefore, it's a possible model for baryogenesis in the early universe. But these are things that we're not going to discuss. I'm just mentioning these so that you know how wide a scope instantons and non-perturbative solutions of gauge field theories have. Okay, so now let's begin at the very beginning. Suppose we have two independent scalar fields that are real, and we'll call them phi 1 and phi 2. And here is the kinetic term, and here is the potential term. The Lagrangian is the kinetic minus the potential. And if the potential depends only on phi 1 squared plus phi 2 squared, well, there's going to be a kind of rotational symmetry over here. Different values of phi 1 and phi 2 will give you the same potential, provided that this over here is a constant. Well, we can let the fields take complex values, and we'll put them into a column vector like this. This 1 over square root 2 is just for normalization. And if you assemble them like that, well, then this becomes a row vector, whereas this is a column vector. You multiply them through, and this is essentially what is above over here, with the difference that now the fields have complex values. Okay, so now suppose that U is some constant, n by n matrix. By a constant, I mean it does not depend upon space and time. And just to, since we want to do the simplest thing, so this U will be something that will act upon this column vector which is just two components over here. I mean, we can do it with n by n, but it's easier conceptually if you do it with n equal to 2. These are unitary matrices. U dagger U is equal to the unit matrix. And now imagine that you were to do a unitary transformation on the phi's. So phi of x is acted upon by U, and this gives you a new phi. Well, if phi goes to U phi dagger then goes to, this deserves to be reversed. Sorry, there's a mistake here. This is, oh no, this is fine. Phi dagger, U dagger is fine. Okay, good. Now, nothing happens to phi dagger phi, because if you multiply phi dagger with phi, then U dagger U is equal to 1, as over here. So phi dagger phi does not change. And since U does not depend upon x, this does not change. In other words, what we have is an invariance of the Lagrangian under the global transformation. By global, I mean that this U, or this U over here, does not depend upon x. Here comes a very important idea due to Yang and Mills, 1973. They were inspired by the success of quantum electrodynamics, and quantum electrodynamics has a very simple symmetry where U is a 1 by 1 matrix, and you can simply write it as e to the I phi. In that case, you can recover electrodynamics by making it invariant under local transformation. So e to the I lambda of x would be a local gauge transformation. So the Yang-Mills idea was to generalize this to unitary matrices whose generators are Lie groups, and all of particle physics now depends on locally invariant gauge theories. Okay, so now suppose that the matrix U does depend upon X. It's unitary, so U dagger U is equal to 1. Then when you make the transformation, phi goes to U of phi, so this matrix U now does depend upon X. Then you see what happens is that d mu phi has to act upon both of these. It has to act upon U and it has to act upon phi. And by the chain rule, this gives you this, d mu U phi, U d mu phi. And if you take the conjugate, well, the conjugate transforms like this. So relative to the previous case, the difference is that this d mu now acts upon the matrix U. Okay? Now, that means that this does not remain invariant. It doesn't become just itself. And it might look as if local gauge invariance is not possible to do. But this is what Yang-Mills said we have to do. Let's invent a new Lagrangian. And they said we're going to define a new object called the covariant derivative. So if you write the Lagrangian now as in terms of covariant derivatives with the potential remaining as before, see, nothing happens to the potential because the derivative is not acting on that. In that case, d mu phi then becomes this. So U now acts on phi. And remember, this is an n by n matrix, and this you can consider a column vector. Okay? So now, if you make this combined transformation, phi changes to U phi, and if you make a mu transform in this way, U dagger A U plus I, and this I is significant over here, U dagger d mu U, then it would take us about 5 minutes to verify this, but basically just put in this new A mu into here, into and then the Lagrangian becomes invariant. Okay, now up to this point, A mu is just something that is dead. It's not. It has no dynamics. So the question is, how will you include this term in the Lagrangian? You can do it by inserting this term, where f mu nu is this. How do you get to such a term like this? Well, basically, it was by trial and error that the invariant Lagrangian was discovered to be this. Okay. No, wait a minute. This U over here has to be A mu. Yes, this has to be A mu over here. So there's a misprint over here. This has to be A mu, and indeed in the previous one. So when I put this on the net, I'll fix it. So this over here also has to be A mu. And then when you make the transformation A mu like this, then you have to then this over here will keep the Lagrangian invariant. Okay, so again I have to fix this here. This will be A mu phi of x. How did Yang-Mills discover this? Well, it was by trial and error, and since this is going to be important for the next lecture, I want to go into a different way by which one can get the gauge terms and discover the invariances. For this, we will have to learn some new mathematics. So the rest of this lecture is going to be just about mathematics and the new ideas that we must incorporate as we learn about gauge theories in quantum field physics. Now, a long time ago, Wigner, no, this wasn't very long, this was 1960s that he said, physics is becoming so unbelievably complex that it's taking longer and longer to train a physicist. It is taking so long, in fact, to train a physicist to the point where he understands the nature of physical problems that he is already too old to solve them. Well, physics since that time has become even more complex. We have to learn now some new mathematics. So what is the old mathematics before I come to the new mathematics? Well, the old mathematics is calculus and linear algebra and differential equations and complex variables, probability theory, group theory. So all this is more than 100, 150 years old. Of course, it is still hard stuff to learn it, but the new mathematics that one needs, especially for string theory and for gauge field theories, less for gauge field theories than for string theory, you need differential geometry, which is basically calculus plus linear algebra. You need differential topology, which is differential geometry and topology. You need some idea of fiber bundles, and then if you are ambitious, then many other things. But new subjects keep getting invented. What I want to give you is just a basic introduction to differential forms, which will be important for us. Of course, the question is whether this stuff actually is useful or not. I mean, why do we need all this mathematics? Well, if you look at Maxwell's paper of 1865, it has, so these are Maxwell's equations. Gauss's law is written like this. You recognize it, of course, because this is divergence of E is equal to minus E. Well, we would have 4 pi rho over here, but okay. This over here would be curl and this. So this is, this is, he says, equivalent to Gauss's law for magnetism. So this would be divergence of B equals 0 in some way. Faraday's law, Ampere-Maxwell law, Ohm's law, etc. Charge continuity, divergence of, which we would write today as divergence of J equals minus d rho dt, written in this way. So Maxwell's equations, which today you learn as 4 equations, was 20 equations in in Maxwell's original papers. Well, then comes Heaviside, and he invents the Heaviside function, of course. He's just a high school graduate, but he invents these symbols, divergence and curl. And therefore, today under Maxwell's statue, you don't have divergence of E equals 4 pi rho. You have something close to that, divergence of D equals rho and divergence B equals rho, etc. This, of course, is the same. But they've written this in a medium, so that's okay. Now, this is a very popular T-shirt. Many of you must have seen. And it's these equations that give you light. And always it is, so even you have mugs like this. And Maxwell's equations are so important in physics that Steven Weinberg had to, he had a comment on this. If you have bought one of those T-shirts with Maxwell's equations on the front, you may have to worry about its going out of style, but not about its becoming false. We will go on teaching Maxwellian electrodynamics as long as there are scientists. And of course, we will go on teaching quantum chromodynamics and quantum electrodynamics, all these gauge theories which are so important, the Standard Model. We don't know about string theory, but we will be teaching these gauge field theories for the next, forever. Okay, so what's the modern way of teaching Maxwell's equations? We start with this quantity, it's called the gauge potential. We then create the field strength tensor from that. So this is the anti-symmetric tensor, which is created from this differential operator and this vector potential. We can create two tensors. One is F mu nu, the other is the dual field tensor, which is F mu nu with a twiddle. And that's got this Levi-Civita tensor multiplying F. Maxwell's equations then become this. D mu on this is equal to 0. And so if you remember, there are two Maxwell equations which are sourceless. One is divergence of B equals 0. The other is curl of E is equal to minus 1 over C dB by dt. So those two are equivalent to this, and this is equivalent to the ones with the source terms on the right side. So it's better. We've got now two equations instead of 4. I mean, we started with 20. Thanks to Heaviside, we went down to 4. With this modern notation, we've come to 2. But we can do better. Because these have indices. There's mu nu, and we need to, indices are always ugly because they depend on your coordinate frame. If you are in one frame, you will need, invariance under Lorentz transformations is nice, but this is not an invariance. It's a covariance. So this is where differential geometry and differential forms can be very useful, and it starts with Riemann more than, well.
Wouldn't Gauss who started it? Wouldn't Gauss be because the theorem of Regium actually came before Riemann's lecture?
Yes, so it wasn't Gauss who started it. Riemann was a very young boy, 19, 20 years old when he came to Gauss. and he said, can you give me a nice problem? So Gauss said, sure. For the last 1,000 years, people have been doing plane geometry where parallel lines never meet, where the sum of the angles of a triangle is 180. I want you to invent a geometry which violates all of this but keeps the basic axiom, the fifth postulate of Euclid, intact. No, the first four intact, but the fifth one is to be modified appropriately. So I suppose you know that Riemann had a nervous breakdown after that. He went back to his village and he was completely shattered, but then he returned and he had the complete geometry worked out. So what is differential geometry? It's about curvature, it's about distances, it's about areas, and these are things that you need even to formulate general relativity. We also need differential topology because, you see, this is a manifold. It's a smooth manifold because, after all, we're doing differential calculus. But there are holes in this manifold, and so you can't get to every place on it, and therefore the question is it what is its topology? So if it has holes, if it has two holes, it's got a different topology from one which has got no holes. Is it a compact manifold? Meaning, is its boundaries included or not? Is it embedded? So if you have maybe there's a higher dimensional space in which it is embedded. So these are issues of differential topology, and on this, Eli Cartan, he put groups at every point on the manifold. Okay, so now finally we come to differential forms. We're going to call this over here a one form. So a mu is just a function. This dx mu is something that, if I make a change of coordinates, will transform according to the chain rule. So nothing very mysterious about that. All we require is that dx mu transform as is normal. So let's take a over here. Now let me transform dx mu. That's by the chain rule dx mu by dx prime nu with this. And now you see it has the same form, provided it looks the same. In that sense, it's the same form. See, this over here will just be defined as equal to this. And so A has not changed what it looks like. What about if I take two of these dx's, if I take two of these dx's, or two of these dx primes? Well, you see, here I will use the property. This is defined to be the property of this thing over here. That property is of antisymmetry. So in one order it is that, reverse the order and you get a negative sign in front. Now if you create this object over here in the following way, that let's say you have a set of numbers. This is a function a mu defined at every point on the manifold. Then this dx mu wedge, so this is called the wedge operation. This wedge, this is called a two form. And again, the important thing is the antisymmetry over here. What that also means is that if I have the same index here as over here, then this will vanish because something will be equal to itself. Okay? Now, just like if I make a change of transformation x to x prime, I'm going to do the same over here. Again, this dx mu will change into this thing over here. This dx nu will change into this over here, and I'll get dx prime mu wedge dx prime nu, and this new thing which will be got from this times this, you could say it's a matrix, dx mu dx nu, two of these, since I'm using the chain rule twice. And so again, this is invariant. So you see, when I make a change of frames or I make a change of coordinates, this thing does not change. And I can create 3 forms, 4 forms, n forms. There's an operation, it's called the exterior derivative. So if D acts on A, it differentiates. So let's say that it acts on a 2 form. So you remember the 2 form is this, A is equal to this. So now imagine that D is allowed to operate on A. In that case, dA will differentiate this, and you will stick on another wedge dx rho over here. So if you start from a 2 form by operating with D, and this is called the exterior derivative, you'll make a 3 form, and you can make a 4 form, and so forth. 4 form from a 3 form. Okay, now this is a particular kind of form. What if I act with D on this? So imagine that on this over here, I again act with a D. Well, that D will act on this. I'll have another index, let's say D lambda, and I have to add on over here wedge dx lambda. But because of the fact that partial derivatives commute with each other, this will be 0. So this exterior derivative has this property that when it acts twice upon a form, it gives you 0. In fact, you can generalize this and say d into d, or d squared, is 0. I'm not going to prove this, but if d acts on a form h and gives you 0, then you can prove that h is equal to dk, but only locally. Doesn't have to be globally. Doesn't have to be everywhere on the manifold. Well, it's easy, of course. If I act with d on h, then I get d squared k, and that of course is 0, but it has to be, it's not true globally. On integration, if I have a manifold and I take dA, then that's the same as integrating the form over the boundary of the manifold. Now this is Stokes' theorem, this is Gauss's theorem, this is all that you have learnt in calculus, and it is all without using any coordinates. No coordinates. No vector operators, no curl, no divergence, no Laplacian, nothing. It looks too good to be true.
But it is the fundamental theorem of calculus.
But it is the fundamental theorem. All this is basically calculus, but in a language so refined, so good, that everything comes out of it very naturally. And so now even you have t-shirts on this. That, well, calculus is equal to topology. Okay, so returning to Maxwell's equations, and we'll use differential forms on this. Let's start with a one form. So A is equal to A alpha dx alpha. And now I will define the field strength as dA. Now why can I do that? Because I know that when I have two forms, then they're antisymmetric. So this is going to be something that's got antisymmetry built into it. Further, that if I act with d on this, I'm going to get d squared A, which is 0. Okay, so this seems to be a very reasonable way to define F. So therefore, you get half of Maxwell's equations for free, the ones without the source. So dF is equal to 0, and now you have only the two Maxwell equations left, which have got the source rho and the source j. Okay, important point to notice over here is that suppose I change A to A plus d alpha. So this exterior derivative acts on any function. A function is a zero form. Okay, let me stick that in over here. Instead of A, I put A plus d alpha, but d squared alpha is equal to 0. And this is what you call a gauge transformation. You change A to A prime, where A prime is A plus, d mu, whatever. Yeah, you can just add a derivative over here. Well, now there are other operations that you can define, and these are called the Hodge star operations. You can have this on a zero form, one form, two form, etc. So the easiest is, a star of A on a four form. So 1, 2, 3, 4, and since we in general can deal, so this is more important for general relativity than for gauge field theories, although even in gauge field theories we do need a metric. We could just put this equal to 1 for flat space, but in general there'll be a square root of minus g. Well, this is the 4 form. With a 3 form, it's defined as this way: 2 form, 1 form, and a 0 form. I can't get into too much detail, but with this definition, these are definitions, and they're definitions made with a very specific purpose. Then let's try and rewrite the Maxwell equations that we know so well using differential forms. So we'd like to use the principle of least action and create an action which is invariant under this gauge transformation. And we would like to couple this to a source term. Okay, so if you take this action, and now this is the integral over the manifold, and if this is the form that you're integrating over, then you see, for one thing, this integral doesn't have any coordinates in it.
Right.
How will we get the equations of motion? We'll minimize this action by making a little change in S. So you make a little change in A, which is A plus delta A, and immediately you get your source-free equation, df equals 0, and then using the Hodge star, you get the other equation. And now here are the Maxwell equations without any coordinates. So true in every frame. You don't even have to talk about which frame, which Lorentz frame you are in. Forget Lorentz frame. It can be an accelerating frame anywhere. It's now frame independent, coordinate independent. From this you can play many games. For example, you could start with A being not just a 1 form, but it could be a P form. And now if you have F over here, then the conserved current which comes from that is itself a P form. And you can make a gauge invariant action in this way. Okay. This will not be directly relevant to gauge fields, but still nice to know. Field binds. Field binds, field is many legs. So this cockroach has many legs. Think of it as walking on a manifold. And of course, it's carrying its legs with it as it goes. By the way, the most common use of the field bind is the tetra, the four bind. What is it in German? I forget. Huh? Field, no, with four legs. Anyway, okay, so here is a curved manifold, and you see it's curved because, well, this is a triangle. It's got negative curvature. Sum of angles is not 0. Parallel lines do not meet. How do you characterize such a manifold? Well, there is the curvature 2 form, which is written this way. So this R mu nu is the Ricci tensor, and you make a curvature 2 form from that. The field bind is actually the square root of the metric tensor. See, square root in the following sense, there are 2 field binds over here. There's this and there's this. So E squared is equal to G. That's the way to remember it. So E is the square root of the metric tensor, of course, with all the indices put right. What are these? These are like little sticks which are carried by the cockroach as it goes around the manifold. Here's a 1 form. So if this is a field bind, this will be the 1 form. And now the connection in differential geometry is what takes you from one frame to the other, and that is the 1 form. So for electrodynamics, A, the vector potential, is the 1 form. I won't get into this, but I just want to show you that how useful these are. You can derive many identities which involve the Riemann curvature tensor, Bianchi identities, etc. So, for example, if you start with this, then you can immediately do this. You use d squared equals 0, then you're left with this. And um, here's an important result, that R wedge, R wedge E is equal to 0. You can get these equations for the Riemann tensor. This is really the Bianchi identity. And you can, in doing general relativity, you can write the Einstein-Hilbert action, which normally you would write as square root of minus GR integral S equals that. And you can do it almost on the basis of reasoning, simple reasoning. Well, you don't want more than 1 power of the curvature. Then the other available form is this. And this finally brings me to nearly to the end of this lecture, which is on non-abelian gauge theories. So here, the connection is really the gauge potential, A. And with this, you can explore not just what happens near a minimum, but you can explore globally the manifold. And this is going to be important because gauge field theories have got an infinite number of minima. And each sector of a gauge theory is specified by a certain topological number called the Chern number. But now let me get into some serious work over here. Those were just words. So if we start with the one form, A, which is this, which you've now seen many times, well, A wedge A is equal to this. Now, you see, this is antisymmetric, which means that I can write it like this. Half commutator A mu A nu. Okay. Now, I am going to create the field strength tensor F, which in the ordinary one that we teach in school, not school, but undergraduates, you write F is d mu A nu minus d nu A mu. Well, that part is just this. But now we're doing non-abelian gauge field theories. So you need a two form. Well, what are the two forms which are available? One is this, the other is this. Now, of course, you could say, this part I know, but what if there was a constant in front? Let's say 2/3 over there. Okay, so admitting that possibility, we can see if you need 1 over there or 2/3 or 5/9, whatever. 1 will be good enough. 1 is what you should have over there. All right, now, suppose I make this transformation. A goes to UA U dagger plus U D U dagger. Then when I make this change, plug it in here, and I use d squared equals 0, and I use U dagger, U dagger, or U dagger U is equal to 1, and I apply d on that, then I get, and I use the chain rule over there. Then in just 1 minute, you will see that F defined this way under this transformation becomes this. So Yang and Mills spent God knows how long trying to figure out what is F mu nu. Here it comes out in just 1 minute. Okay, so if you write this in terms of, so these are matrices over here. This matrix goes into this. But if you want to project out, if you want to put in indices, then of course this is this, and then just put in the indices, that's that. After this, it is trivial to make a gauge invariant Lagrangian. All you do is you put this and it's Hodge star. Whatever there's here, you put its Hodge star, and this then becomes invariant under this transformation. So you see, it's as if it's so amazing that everything simplifies. Now, the thing is that if A is to be understood as a connection, what is the connection? A connects one frame with another, one set of coordinates with another. But then what is the space? Because look, A is a matrix. It's not a function. In abelian in abelian theories, it's just a function. So this is what gives you the local gauge invariance, the connection. But for us, we have to ask, in what space does A live? And the answer is that it lives on a fiber bundle. So here is our basic space-time, x mu. At every point x mu, you can think that there is a fiber that runs up, and there are matrices that live on this. And so that answers the question: what is the manifold on which these connections live? Well, this is just about all pretty much. So there's this base space, and at each point there is this fiber. And now the space can have all kinds of different topologies on it. So this is it, and we will now stop this quick review of advanced mathematics that's needed for gauge theories. But why is any of this useful? And this is something that Wigner asked, I think in the 1950s. He wrote this paper, The Unreasonable Effectiveness of Mathematics in the Natural Sciences. You don't know why these concoctions of the mind, these inventions of the mind, will have anything to do with physical reality, but they do. We are still trying to figure out what that reason is. So anyway, this is a great philosophical puzzle, not with a clear resolution. Then, we physicists also have to do calculations, and we can't spend too much time on philosophy. We'll just take what mathematics there is. If it's useful, we'll use it. If not, let the mathematicians play with it. Okay. Good. Questions? Any?
So in the second last slide, where you exemplified the fiber bundles by drawing out some, lines over base space, there were some horizontal lines that were not connected to the base space. So, or they are also the connections.
No, they are all connected to the base space. At each point on the base space, there is a fiber.
Okay, but the vertical lines are connected because they have base connected to the base space. But the horizontal ones, are they connected to some other point?
That's comparing fibers on some curve. So you could be looking at the manifold at one time and then at another time. So time slicing,
Oh,
perhaps. Yeah.
okay. So these the horizontal ones are the connections so the horizontal ones are the fibers at some other
Yeah.
times. Okay,
Yeah.
okay.
Yeah.
So and next, when we call a mu or the gauge potential a connection, so what is the motivation behind it? Any physical observable? I mean, in if we talk about QED or the Maxwell equations, there is magnetic field, there is electric field. There are also components of some for vector or some component of some vector. Why are we calling a mu connection?
That's the name it has always been given. The gauge potential is sometimes called connection, sometimes called gauge potential. Why is it the connection? Because it establishes the 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 quantities in one frame and a nearby frame. So, in that sense, I think this is an appropriate name. You're asking me why it has that name.
No, I'm just asking when we do transformation in gauge field, the transformation requires us to like have a mu in our Lagrangian. So it is connecting this point and a transformed point. So I mean, I understood that this is the basis of why we are identifying a mu as connection, because it is connecting a space-time point x to where it is being transformed, because it is appearing in our the covariant derivative.
Yes, so the connection appears in the covariant derivative. It is what is needed to make the Lagrangian invariant. And so it connects one transformation with another.
So the last question was when we said d square is equal to 0, d square of any like a is equal to 0.
Yeah,
So you use the commutator.
yeah.
So it it went to 0 and the whole thing goes to 0. So it has to be anti-symmetric, right? Because
Yes,
then you can make it anti-commutator and that goes to 0.
right,
Okay. That's
right. So if I take dA, well, that is d mu, a nu, and then I have to have a wedge over there. Okay, then I act again on d, and I'll get a partial derivative, but the partial derivatives commute with each other, and that will make d squared, acting on dA equal to 0.